Have you ever wondered about the nature of reality and the universe? Is everything as it seems, or are there hidden layers of complexity that defy our understanding? In the world of the minute and the invisible, reality behaves in ways that baffle and amaze. Here, in the realm of quantum mechanics, particles don't just exist, they entangle. This entanglement, a mysterious and counterintuitive phenomenon, is a unique correlation where the state of one particle is directly tied to the state of another, regardless of the distance that separates them. The quantum world challenges our classical intuition, revealing a profound interconnectedness that governs the behavior of particles. It's a world where changing the state of one entangled particle instantaneously influences the state of its entangled counterpart. Welcome to a journey into the fascinating world of quantum entanglement, where particles dance in an intricate, mysterious ballet. Our story begins in the early 20th century, with the birth of quantum mechanics. This revolutionary theory emerged as scientists wrestled to understand the bizarre behaviors of the smallest constituents of matter. Amidst this struggle, the concept of quantum entanglement emerged, a phenomenon that would challenge our understanding of the very fabric of reality. Quantum entanglement was born out of the mathematical formulations of quantum theory. It describes a peculiar correlation between particles, suggesting that the state of one particle is intimately tied to the state of another, regardless of the distance separating them. This puzzling prediction of quantum mechanics baffled scientists and philosophers alike. In the year 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment, known today as the EPR paradox, to challenge the completeness of quantum mechanics. They argued that the eerie correlations implied by quantum entanglement suggested the existence of hidden variables that determined the properties of particles. According to their view, quantum mechanics was incomplete, and a more profound theory was needed to unveil these hidden variables. However, subsequent experiments would challenge this perspective. In the mid-20th century, physicist John Bell proposed a set of inequalities, known as Bell's inequalities, that could be tested experimentally to distinguish between quantum mechanics and theories with hidden variables. Remarkably, these experiments confirmed the predictions of quantum mechanics, revealing a world far more intertwined than we could have ever imagined. These experiments demonstrated that the world of quantum mechanics is inherently non-local. Changing the state of one entangled particle instantaneously affects the state of its entangled counterpart, a phenomenon Einstein famously referred to as spooky action at a distance. This realization has profound implications for our understanding of reality. It suggests that the universe at its most fundamental level is deeply interconnected, with particles capable of influencing each other across vast distances instantaneously. As it turns out, the universe may be far more interconnected than our classical intuition suggests. The story of quantum entanglement reminds us that the universe is a far more mysterious and fascinating place than we could have ever imagined. But what exactly is this quantum entanglement we're talking about? Well, it's a bit like a cosmic dance, where two particles, no matter how far apart, move in perfect harmony. Imagine two dancers spinning in unison. Even if one dancer were to suddenly jet off to the other side of the universe, their dance partner would instantly know and adjust their steps, maintaining their synchronized dance. This is the magic of quantum entanglement. Quantum entanglement occurs when two particles become linked, and this connection enables them to instantly affect each other, regardless of the distance between them. This isn't a normal physical connection like a string or a beam of light, but rather an invisible, instantaneous link that exists in the strange and counterintuitive world of quantum mechanics. To understand this better, let's delve into the concept of a quantum state. In quantum mechanics, particles are described by a wave function, which encodes all possible states a particle can be in. When two particles are entangled, they share a joint wave function. This means the state of one particle is directly tied to the state of the other. The fascinating part is, this shared state persists even when the particles are far apart from each other. If you change the state of one entangled particle, say by measuring its position or momentum, the state of its entangled counterpart will also change instantaneously. This is the spooky action at a distance that Einstein famously referred to. The spooky part is that this change occurs faster than the speed of light, defying our classical understanding of how information should travel. This doesn't mean that quantum mechanics is breaking the speed of light limit set by Einstein's theory of relativity. Rather, It suggests that at the quantum level, the universe is deeply interconnected in ways that our everyday experiences can't quite capture. This spooky action at a distance, as Einstein called it, remains one of the most intriguing aspects of quantum mechanics. It opens up a world of possibilities and challenges us to rethink our understanding of reality. Quantum entanglement isn't just a theoretical curiosity, it has practical implications too. Quantum mechanics, as mystifying as it may be, isn't just about baffling scientists and challenging our understanding of reality. It's also about harnessing these strange phenomena for practical use. Quantum entanglement, in particular, holds enormous potential for revolutionizing both computing and communication. Let's first dive into quantum computing. Traditional computers operate using bits, which can either be 0 or 1. Quantum computers, however, take this a step further. They use quantum bits or qubits, which can be both 0 and 1 at the same time. This is possible because of a property inherent in quantum mechanics called superposition. But it's the entanglement that truly sets quantum computing apart. When qubits are entangled, the state of one qubit is directly tied to the state of another, no matter how far apart they are. This allows quantum computers to process a vast number of possibilities all at once, making them exponentially more powerful than even the most advanced classical computers. Now let's turn our attention to quantum communication. This is where things get really interesting. Quantum communication leverages the power of entangled particles to create a secure communication channel. In a process called quantum key distribution, entangled particles are used to transmit information. The beauty of this method is that any attempt to intercept the communication would disrupt the entangled state of the particles and immediately become detectable. This makes quantum communication potentially unhackable, offering a level of security that is simply unattainable with classical methods. So, from supercomputers that could potentially solve problems deemed impossible today, to unhackable communication systems, the practical applications of quantum entanglement seem limitless. It's like we're at the cusp of a technological revolution, and quantum entanglement is leading the charge. Indeed, the future of computing and secure communication may very well hinge on our ability to harness this quantum weirdness. Quantum entanglement doesn't just challenge our scientific understanding, it provokes deep philosophical questions too. It invites us into a vibrant discussion about the nature of reality and the role of observation, a debate that transcends scientific circles and engages philosophers, thinkers, and curious minds alike. Quantum entanglement, with its spooky action at a distance, as Einstein famously phrased it, disrupts our conventional understanding of separability and locality. It suggests a profound interconnectedness in the universe that defies classical intuition. If two particles, no matter how distant, are instantaneously affecting each other, what does that say about our concept of space and time? This phenomenon also questions the role of observation in determining reality. In the quantum world, it's not until we measure an entangled particle that its state becomes definite. But does this mean that reality is dependent on our observation? Are we, as observers, actively shaping the universe just by looking at it? These are not just abstract musings, but questions that arise naturally as we grapple with the counterintuitive principles of quantum mechanics. Then, there's the matter of hidden variables, proposed by Einstein, Podolsky, and Rosen. They suggested that the seemingly random behavior of quantum particles could be explained by unseen factors. Yet experiments have largely refuted this idea, reinforcing the inherent randomness and non-locality in quantum mechanics. This conclusion further challenges our classical notions of causality and determinism. Quantum entanglement also raises questions about information transfer. If the state of one particle can influence another instantaneously, are we witnessing a form of communication that surpasses the speed of light? Or is there a deeper level of reality that we are yet to comprehend? All these debates remind us of the enigma that quantum entanglement is. They make us question our understanding of the universe and our place in it. Quantum entanglement doesn't just redefine particles, it redefines our perspective. So as we delve deeper into the quantum realm, we're forced to reconsider our very notions of reality itself. Quantum entanglement, then, is a truly remarkable phenomenon. This mind-boggling dance of quantum particles, with their states intertwined no matter the distance, shatters our conventional understanding of the world. Born out of processes like spontaneous parametric down conversion, these entangled particles exhibit a spooky action at a distance, as Einstein poetically put it. The EPR paradox and subsequent experiments, such as those by John Bell, have further illuminated this quantum enigma, revealing the inherent non-locality and entanglement of particles. The practical implications are just as compelling, with quantum computing and communication leveraging these unique correlations for computational power and security beyond the reach of classical systems. Even teleportation, once a realm of science fiction, finds a footing in reality through the transmission of quantum states. Yet, despite these strides, quantum entanglement continues to provoke philosophical debates, challenging our perceptions of reality and the universe's fabric. As we continue to explore this enigmatic dance of quantum particles, who knows what other secrets the universe might reveal to us?